Um, B8. I think we're past everything that everybody had question, like the main questions that people had had. No, we're not. We've only gotten through three problems. Oh man, A4 is the last one that I'll do through. So that way we've gotten through everything that we need to get through. So B8, I don't think you guys really covered necessarily how the relationships of the equilibrium expressions kind of can be manipulated and changed around, right, to figure out what KEQs are going to be if you know them for like certain reactions and how they kind of stack up. So in this case right here, right, what we can do, right, we're given two different reactions, right? So the conversion of N2 and O2 into NO or into NO2, right, and we're given the equilibrium constants, right, the K values in both of those cases, right? And so if we look at those K values, right, they're incredibly small, right? Times 10 to the negative 31, times 10 to the negative 18, right? They're not really going to be favored to be occurring. But excuse me. Right, but we can kind of manipulate those things to figure out like new K values and stuff like that. So part A says write the equilibrium constant expression for the formation of 2 moles of NO at 25 degrees Celsius, right? So looking at that reaction, right, what we have is that K in this case is going to be equal to the partial pressure of NO squared over the partial pressure of N2 times the partial pressure of O2, right? So that's to form 2 moles of NO, right? So that's what that expression right there looks like in this case. For B, right, it says calculate the KQ for the decomposition of 1 mole of NO at 25 degrees Celsius, right? So looking at that first equation, right, what we can see is the, that's the formation of NO. So the decomposition of NO should go in the exact opposite direction, right? So the decomposition reaction would then be 2NO to form N2 gas plus O2 gas. Now, a very important thing, right, to think about is that the way it's currently written, right, is that you have 2 moles of NO gas in this case, right, forming 1 mole of N2 and 1 mole of O2. The equilibrium, right, is going to change if the concentrations, right, of the different parts are altered in those cases, right? And so if we're doing 1 NO, right, so if we're going to take that right there and we have to divide it by 2, right, we then end up with 1/2 N2 and 1/2 O2. And so now if we write out what the the K value is in this case, right? So now the K value for this reaction is going to be equal to the pressure of NO over the pressure of N2 to the power of 1/2 times the pressure of O2 to the power of 1/2, right? So that's what that expression there is. So if we kind of, think about what's that relationship to that initial K value that we have in these cases, one thing that we know is that it's now flipped. And so this is going to then be equal to, right? So this is, so I'll just call this KP1 right there, right? Just to keep things simple, right? So the K for this new reaction now is going to be equal to KP1, but to the power of -1, right? Because we're going to flip it, right? It's just simply the inverse. It's, 1 over what we have in those cases. But the thing is, too, is that because we divided it in half, right, essentially everything then, had the square root of it taken, right? So now it just simply becomes, instead of -1, right, it becomes the -1/2 in that case. And so all we have to do is just simply take this number, right, and we plug that into here, and then we can calculate what the new KEQ value is for the decomposition reaction of 1 mole of NO gas versus it being 2 moles of NO gas. So if we do that, right, we have 4.2 times 10 to the negative 31, right, and then that's the power of -1/2. What we get is 4.2 times 10 to the negative 31, and all of that is to the power of -1/2. What we get is let me just pull it up. Yeah. 1.54 times 10 to the 15. in that case, right? Which matches what I have on the key, right? And so that's the relationship there, right? Is that if you know the K in one direction, right, you can easily figure out what the K in the other direction is by just simply taking the inverse of it, right? So to the power of -1. If the coefficients change, right, all you have to do is to make sure then that you alter how those, are being changed again in the exponent of the K value in that case. And so we can use that same logic for part C, right? So now we're talking about the decomposition of 1 mole of NO2 at 25 degrees Celsius. So it's the exact same approach, right? Because again, if we're looking at that reaction, right, the decomposition reaction in this case, is 2 moles of NO2 gas, right, going here and then forming N2 plus O2 gas, right? So typically it's 2 and 2 in this scenario, right? But now again, we're only looking at it for being 1, so we divide all of those by 2, so that gets divided by that gets divided by that, right? This gets divided by 1/2 in this case. And so now if we look at this K expression, right, we have the partial pressure of, oh, wait, this is also wrong. Sorry. This should be P N2 to the power of 1/2 over P of O2 to the power of 1/2 over P of NO. Right, so you get then the P N2 to the power of 1/2 P to the power of O2 on its own, and then P to the power of NO2 on its own. So again, it's a very similar thing where now it's going to be then the Kp of 2 now that we're going to be plugging in here. And again, right, because we flipped the reaction, right, so this is now going to become negative. And because again, right, we divided all the coefficients by 2, it becomes the square root. So it's 1 over 2 in that case. And so we plug in our numbers that we have. So we have 1.0 times 10 to the -18 to the power of 1 over 2. So that becomes 1 times 10 to the -18 1 over 2. And so that becomes 1 times 10 to the -9 in that case. Oh, I messed up. I forgot the negative in the 1 times 10 to the -18. Right, so that becomes 1 times 10 to the 9th. Sorry, in that case right there, right? So, looking at that right there, the decomposition reaction of 1 mole of NO2 can be, calculated that way as well. Now, if we, again, as I had mentioned, right, if you know the Kp values, or if you know the K values for, a bunch of different reactions, and you're trying to figure out, well, what's the equilibrium then as you're going from one thing to a different thing, you can actually put all of those together and mathematically then figure out what they are just from the Ks, right? You don't have to go through a different series of calculations and stuff like that in those cases. And so, to calculate now, what we're looking at is the decomposition of 2 moles of NO2 to form 2 moles of NO gas and 1 mole of O2 gas at 25 degrees Celsius. And so looking at this right here, right, we can just write out what the K expression is for this reaction. So that's going to be, right, the pressure of NO gas squared, and then the pressure, to the power of 2, and then the pressure of the O2 gas over the pressure of NO2 gas squared as well. Right, so that's right there what the K expression is. That basically comes out to being, the decomposition reaction of NO2 times, right, the equilibrium expression for the formation of NO gas, right? So if we just simply take those two together, right, we can just simply say, taking the NO gas formation one, right, so this is then going to be P NO gas squared over P of N2 gas times P of O2 gas, right, times, and now, right, we're gonna be looking at the decomposition reaction, but of 2 moles, right, not of 1 mole, and so that becomes, P of N2 gas times P of O2 gas squared, right? Because you're going to be forming 2 moles in that case, right? Over P over NO2 squared in that case, right? And so we have all those different parts right there, right? And so then, we can prove to ourselves that just simply multiplying those 2 different parts, by each other gives us our values, right? Because then these pressures cancel out, right? This cancels out, the square right here cancels out, and so we end up with what we want is our equilibrium expression there. So what that means in terms of the K values that we were given is that this is, this right here was equal to Kp 1 right here, right? And we can multiply that then by the Kp of 2, right? But the inverse of it, right? Because we flipped it in this case. Right? And so those 2 come through there. And so all we have to do now, we can plug in our numbers. So we have 4.2 times 10 to the negative 31 times 1.0 times 10 to the negative 18, but that's the power of negative 1. And so what that comes out to is 4.2 times 10 to the negative 31 times 1.0 times 10 to the negative 18 to the power of negative 1, right? That comes out to being 4.2 times 10 to the negative 13, right? And that's how you can stack essentially equilibrium constants on top of each other, right? So because you can just start multiplying them with each other if you're able to cancel things out, and if you have to, if you end up having to multiply them to be able to get them to for the final expression to match in terms of all the coefficients, right? I mean, you have to then either take the the squares of the Kp values, or take the square roots, or whatever equivalents in those cases, right? And so you can use all of those different things to kind of maneuver your way through figuring out what the equilibrium constants are going to be for reactions that kind of stack on top of each other. And I think that's kind of where oh no, that's not A4. I'm thinking of a different problem.